Okay, hello and welcome to the session 8B, AI for Weather and Climate, Part 8. And please address your questions to Slack channel number 3, Weather and Climate, and we'll try to have answering questions at the end of our session. And when 3 minutes will be left for your talk, I will tell you. And I think now we can start. Our first highlighted presentation will give you an Haupt from NCAI. Welcome, Sue.
Thank you, Vladimir. Today I'm going to talk about some work we're doing at NCAI using deep learning to downscale from the mesoscale to the microscale in complex terrain. The first thing I'd like to do is to really acknowledge all my co-authors. In particular, Susan Dentling has done the bulk of the modeling, and Tom Brummett has done the bulk of the data preparations, very important to this talk. So first, a little bit of context. NCAR and 3 DOE labs have been working together for the past several years to couple the mesoscale to the microscale. So basically using models like the Weather Research and Forecasting model at the mesoscale and using either WRF-LES or standalone models at the microscale. And there are a lot of issues in doing this that we have to deal with, spanning that terra incognita between the two scales, making sure we have consistent surface boundary conditions, initializing the subgrid turbulence at the microscale, etc. But when we get to complex terrain, it gets very complicated if we want to do high resolution simulations. For instance, we've been doing simulations in the Pacific Northwest. There were experiments as part of the Wind Forecast Improvement Project, and we have done lots of simulations, such as this example by our KNNL colleagues, where we can model in the lee of Mount Hood, see the rich flow, and then look at it at very high resolution on the order of tens of meters. So that has been the goal, to even include turbulence as far as we're able to get. And I wanted to show you this one simulation that was really a challenge simulation done on the Cheyenne supercomputer at NCAR several years ago. And it took several weeks to accomplish this 30-meter resolution simulation on 8640 cores. So it's obviously very computer intensive, but we do get this rich behavior, meandering wake that turns into breaking Kelvin-Helmholtz waves, standing waves along Mount Hood, gravity wave shedding, there's cold pools in the valleys, very rich behavior, but very expensive. So a question is, can we use machine learning methods to downscale from order of a kilometer down to 30 meters? That's a 32 times downscale in complex terrain, capturing the rich turbulence of the flow. And to do that, we're going to use the eastern portion of that simulation we just saw, where we've captured frames every 3 minutes. And the method we're going to use is the Enhanced Super Resolution Generative Adversarial Network, or ESR GAN. And this work is inspired from work at NREL that we saw last year, where they took climate model data at 100 kilometers and downscaled to the mesoscale at 2 kilometers. And seeing that success inspired us to try it at the mesoscale to microscale. So first, what is a generative adversarial network? You can think of it as really two types of networks. First, a generator. That is, the idea there is to take the low resolution input fields and to produce the fake or counterfeit high resolution data. Very cheap to do this once you've trained it, but it's not real data. Now, how do you tell whether it's close enough? And that's where the discriminator comes in, where it judges whether it is real data generated by that 30-meter resolution WRF LES run, or whether it's a fake produced by the generator. And by doing this two-step process, we can get more details in that fine resolution generated case. Okay, now, as with any type of machine learning method, it's very important in posing the right cost function. Here we have discriminator loss functions and generator loss functions. For the discriminator loss, the primary thing we want to do is judge the difference between the real and the fake data, where here in the log loss way that we're using, if it is real data and judged as real data, then of course it gets a low loss, which is good. And same if it's fake data judged as fake. However, if it's wrong, then it penalizes it with a higher loss. But we're also experimenting and finding that it's helpful to use this relativistic average loss function as well, where in addition to characterizing the correctness in terms of did it get the real or fake, but also looking at how far relatively from the generated data that the real data is. So doing that type of loss has really helped stability in the algorithm. Now, the generator loss function, the first term of it is typically a content loss. That's where you judge the difference between each pixel, in this case, grid point data, between the simulated or the generated data versus the real WRF LES output. That's the primary loss, but then we add in an adversarial loss that is based on that discriminator probability that we saw on the prior slide. Now, you can also add in weighted other components, things like perception loss, that is trained from previous network discriminator network, or you can bring in physical variables. For instance, in this problem, we're studying the impact of adding things like divergence, vorticity, skewness, kurtosis to get that fine scale detail. Okay, so training data. We have an input resolution of that simulation of 30 meters. We're giving the three components of the wind field, U, V, W, using 7 vertical levels because we care about wind energy. It's over the rotor blade, which is about 30 meters to 160 meters. 7 levels, because it's barotropic flow, we end up with high correlation. So to do that, we're using random offsets to produce tiles that are 512 by 512 grid points. And this is out of the whole eastern half of that simulation where we have the rich behavior that was originally 3,000 by 3,000. Now, the idea is we want to coarsen the field from this 30-meter resolution on the far right to 960 meters to get a 32 times step in, so that we can take the 960 as input data and see if we can recover the 30 meters. Now, we find that adding an extra step, so we're doing a 4 times 8, is very helpful here. And this gives us about 55,000 sets of training tiles, the 960 and 30, and then leaves about 18,600 independent tiles for testing. So network structure, just simplest first thing we tried was just going directly from the 960 meter down to the 30 meter simulation. As you can tell, the results aren't really satisfying, and that's why we decided to do it as a two-step process. First, going down a factor of 4, and then follow it by a factor of 8 to get a total of a factor of 32. And that's where we're getting some very promising results that we've been happy about pretty recently. So looking at a few of these results in more detail, on the left, we have the full domain of the 960 meter coarsened data that we used for training, matching with the 30 meter fine resolution. And when we take one of these 512 by 512 tiles, apply the generator that we have trained together with the discriminator, and we see that we are able to recover this rich texture in the V velocity field. Now, what about the other fields? Okay, U, we're going to look at the second tile in terms of U velocity. Again, we're getting the detail in this part of the meandering wake in the lee of Mount Hood. And we're seeing the turbulence generated and the structures that we expect to see from the original high resolution simulation. And also in terms of the vertical component, we're able again to see some rich structure underlying so that we are confident. Now, what about when we look at them side by side? On the far right here, for each of the UVW components, we see the original Thank you. The original WAR simulation at 30 meters. On the left is the coarsened input data at 960 meters. And we're seeing our ESR GAN results here in the middle. And you see how close the behavior is to the original WRF data. You know, very impressive results. We've been pretty happy to see these. Now, once we have the generator, even on these 512 tiles, we can apply it across the entire domain. So if we then do that, here's an example for our V velocity across the entire domain, comparing it with the original WRF LES simulation at 30 meters. Again, it's really hard to tell the difference. In fact, we asked some of our scientists to ask which was generated and which was the original LES, and they can't tell the difference. The same in terms of the U and the W component. Okay, so of course we've learned a lot along the way. This is very much work in progress, but we are very heartened to see that the ESR GANs do appear to be a very feasible method for downscaling. What you haven't seen in this talk is the tons of simulations that Sue Detling has done in trying to train this, trying to gauge, best weights, best loss functions. It really is a bit of an art to train these systems. And it does require a lot of work, but once you get them trained, you can use transfer learning to apply them to something else. And we are finding it's been successful at downscaling from about 1 kilometer down to 30 meters. It's very plausible, and it's much, much faster than those physical simulations at that high resolution. So we can see that it could be very useful. Okay, we're just starting to add the physical quantities like vorticity, divergence, skewness, kurtosis to the loss function. We can additionally add more input variables like temperature, terrain height or ruggedness, etc. Right now, we've been testing on test data held out from the single simulation, but we wish to test on other simulations as well, and also see if we can use this as transfer learning for other regions beyond this Pacific Northwest case that we've seen. And for that, we're expecting that some of these physical variables could be useful. So thank you.
Thank you very much, Sue. Very interesting, very impressive talk. Thank you. So our next speaker is Lagerquist, I'm sorry, from NOAA. He will present his talk about emulation of radiation. Welcome, Ryan.
Thanks. Can you hear me?
Yes, we can hear you.
Great.
Sounds good.
Okay. So my talk today is on using a UNet++ for emulation and acceleration of a radiative transfer model. I'd like to acknowledge my collaborators on this project, Dave Turner, Ime Uphoff, Jeb Stewart, Vineeta Haggerty, and Christina Kumler. So I'll start off with some motivation for tackling this radiative transfer problem with machine learning. So to start off with, when radiation propagates through the atmosphere, heating occurs in areas of radiative flux convergence and cooling occurs in areas where the radiative flux diverges. So that's why it's important and needs to be resolved in numerical weather prediction, or NWP. But in NWP, radiative transfer is a subgrid scale process, so it has to be parameterized with a separate radiative transfer model. The most accurate radiative transfer models are the line-by-line models, but these are much too computationally expensive for NWP. They're about 1 trillion times too slow to run in operational mode. So in practice, we use simpler radiative transfer models like the rapid radiative transfer model, or RRTM. The RRTM emulates line-by-line models, treating the shortwave and long-wave parts of the spectrum separately. And this figure on the right-hand side is showing what a line-by-line model looks like. So it simulates absorption by every single gas in every relevant spectral band, which we just don't have time to do in real-time NWP. So when used in NWP, a radiative transfer model has to predict 3 output variables. There's a profile of radiative heating rates, there's the surface downwelling flux, and the top of atmosphere upwelling flux. So you need radiative heating rate at every height, and then you just need downwelling flux at the surface and upwelling flux at the top of the atmosphere. For the RRTM, those 2 flux components are accurate within about 1 watt per square meter, while the heating rates are accurate within about 0.1 kelvins per day. So when using the RRTM to emulate the line-by-line models, although it's faster than line-by-line models, the RRTM is still too slow to call it every time step in NWP. So although the purpose of the RRTM is to speed up radiative transfer modeling, it's still too slow to call it every single time step. So we use machine learning, which people have been doing for about the past 20 years, to emulate the RRTM. So we need to speed up radiative transfer modeling even more. So specifically, what we're doing is using machine learning to emulate the shortwave part of the RRTM. We plan to use a similar framework for emulating the longwave part of the RRTM, and I'll talk about that later in future work. So there's a few characteristics of our machine learning approach that make it unique from previous work. One is that we use deep learning. Specifically, we use the UNet++. Deep learning excels at exploiting and predicting spatial patterns, as many people in this room probably know, since it's an AI conference. The second thing is that we make the UNet++ knowledge guided. There's 3 augmentations we've made to the standard UNet, which I'll talk about in section 3, that make it knowledge guided. And the third thing is that we emulate the RRTM, whereas previous groups have emulated the RRTMG, which is the RRTM for global climate models, which is a less accurate version of the RRTM. I apologize for the invite thing that keeps popping up on my screen. I don't know how to make it go away. So now I'll talk about the input data for our machine learning. So like the RRTM, our UNet++ assumes horizontal independence, so it treats each vertical column of the atmosphere separately. The inputs, or predictors, for both the RRTM and the UNet++ are coming out of the rapid refresh numerical model. We extract 0-hour analyses from the rapid refresh model of 14 different variables at 30 different sites. Those 30 sites are shown in the map at the bottom, and the 14 variables are listed in this table here. The first 2 variables are scalars. One is solar zenith angle, another is surface albedo. And then there's profiles defined at every single model level in the RAP. There's 73 different model levels. Those profiles are state variables like temperature, pressure, then variables related to water vapor like specific humidity, relative humidity, the downward water vapor path, and the upward water vapor path. Then we have variables related to liquid water and ice water as well. So we're currently emulating a simplified version of the RRTM, which ignores aerosols, trace gases, and the effective radii of ice and liquid particles. It assumes climatology for all of those things. but future work will allow these predictors to vary and emulate the entire RITM rather than the simplified version. And we're already beginning that future work, which I'll talk about later. So we split the data into training, validation, and testing. The training is years 2018 to 2020 at the non-tropical sites, which are purple and green in this map at the bottom. The validation data is 2017 at the non-tropical sites, so a different year. And then the testing data is 2017 at the tropical sites, which are in orange. So going from the training to testing data, we're testing the generalization ability of the model in both space and time. And we're also testing spatial generalization in a pretty extreme sense. We're testing the generalization to a completely different region of the globe. So training and validating on mid-latitude and Arctic sites, but then testing on tropical sites to see how well we can generalize. So the target variables from the UNet++ are those that an NWP model needs from its radiative transfer model. So that's a profile of heating rates, the downwelling flux at the surface, and the upwelling flux at the top of the atmosphere. The labels or ground truth, which we treat as correct answers, come out of the RRTM because the UNet++ is emulating the RRTM. And on the right-hand side here, I'm just showing for one case, most but not all of the predictor variables. So panel A is showing some of the predictors related to water vapor. Panel B is showing stuff related to liquid water. Panel C is showing stuff related to ice water. In this case, it's 0 throughout the entire column, so it's a bit boring. And panel D is showing the profile of upwelling flux and downwelling flux, and also the profile of heating rate in orange. So here, I don't have time to go into all the components of our UNet++ architecture, but for people who want to know the details, it's up here. The benefit of the UNet++ is that it has more skip connections than the UNet, which are these dashed gray arrows. And those skip connections allow for better preservation of high resolution information. So that's why the UNet++ often performs better than a vanilla UNet. In our case, we found that the UNet++ outperformed an equivalent UNet for profiles with multi-layer cloud, where radiative transfer is the most complicated. For profiles that don't have multiple cloud layers, we found that the UNet++ and the vanilla UNet are quite similar. You can see details in a paper that we just recently published in JTAC. So I'm going to talk about knowledge-guided machine learning before I show you some results. So we've come up with 3 ways to make the UNet++ knowledge-guided. Knowledge-guided machine learning is more trustworthy and has been identified as a key priority in applications to geoscience by a couple of recent position papers. So the first thing we do is we introduce this loss function to ensure physically consistent and skillful predictions of net flux, in addition to surface downwelling and top of atmosphere upwelling flux. So the 3 flux components are related by this equation here, and we gave fnet, net flux, its own output neuron so that net flux can be included in the loss function. We could also satisfy this equation by just post-processing, so we could let the neural net predict surface down flux, TOA up flux, and then we could compute net flux later outside of the UNet. But that post-processing approach leaves net flux outside of the loss function, and we found that allowed the UNet++ to make bad predictions of net flux despite making good predictions of the 2 components on the right-hand side. So the approach that we've taken forces the UNet++ to make physically consistent and skillful predictions of all the 3 flux components. The second thing we do to make the model knowledge guided is we use a custom loss function to emphasize large heating rates. Because large heating rates are quite rare, the distribution is really heavily skewed, as you can see here. But large heating rates are very important for weather and climate, for example, in the maintenance of big stratocumulus cloud decks off the west coast of continents. So we use this equation here as the loss function for heating rates. And basically, I'm not going to go through every term of this equation, but we call it the dual weighted mean squared error, or the dual weighted MSE. So this term, this max function, is the weight. So it gives a large weight to examples with a large actual heating rate or a large predicted heating rate. So this just gives the UNet++ a little extra incentive to do a good job of predicting large heating rates. And finally, the third thing we do to make the model knowledge guided is we use custom predictors to account for non-local effects. There's non-local effects that occur when the heating rate at a given height Z is affected by predictors far away from height Z. So I've given this example here. where there's a case with multi-layer cloud. So on the top panel, if you look at the orange curve, which is liquid water content, there's 2 spikes because there's 2 cloud layers. And the top cloud layer attenuates most of the solar radiation. So most of the solar radiation never gets through the top cloud layer and reaches the cloud layer below. And because these 2 cloud layers are quite far apart in grid cell space, they're about 15 grid cells apart. If you don't include custom predictors to account for these non-local effects, then the UNet++ does a bad job of predicting them. So we included, in addition to concentration profiles for the 3 water species, we added 6 more predictors, which are height integrated paths. So downward and upward integrated liquid water path, ice water path, and water vapor path. We found that that was necessary to really get the heating rate profile correct in these cases with multi-layer cloud. So here I'm showing results based only on the testing data. These are tropical sites in 2017. Here I'm showing the attributes diagrams for the 3 flux components. So there's surface down flux, top of atmosphere, upwelling flux, and net flux. In an attributes diagram, the important thing is that this reliability curve in orange is inside the positive skill area, which is the blue shaded area, and you want it to be as close to the 1-to-1 line as possible. So in this case, all 3 attributes diagrams are looking very good for the 3 flux components. Here I'm showing error profiles for heating rate. The main thing I want to focus on here is panel D, because I don't have too much time left. So there's in panel D, you'll see that at almost every single height, there's an absolute bias of less than 0.1 kelvins per day in the predicted heating rate, and that's considered a threshold for stable use inside NWP. So the absolute bias has to be less than 0.1 kelvins per day. Otherwise, you can't put a radiative transfer model inside an NWP model. The only exception is in the upper stratosphere at 46 kilometers above ground, where the climatological heating rate is highest at this height out of all the heights due to ozone absorption. Here, the absolute bias is a little bit greater than 0.1 kelvins per day. And here I'm showing height-coded reliability curves for the heating rate, and you'll notice that at every single height, the reliability is nearly perfect, even on the testing data, which come from tropical sites, which weren't used in the training or validation. Here, I'm again showing attributes diagrams for the 3 flux components, but now they're split by cloud regime. So there's cases with, this is only liquid cloud regime. So there's cases with no cloud, multi-layer cloud, and single layer cloud. And you'll notice that the reliability for all 3 flux components is really good, with this one glaring exception at the extreme end of low predictions.
Left.
Thank you. And if you go from this slide to the next, this slide is showing what happens with the UNet++ that we decided on, which is trained with a custom loss function to make sure that the 3 flux components are physically consistent and skillful. If we don't do that, you'll notice that the attributes diagrams generally get worse. This one problem at the extreme end for single layer cloud goes away. So that does get better, but everything else generally gets worse. The reliability curves get further away from the 1-to-1 line. So I guess I'm running out of time here. The last thing I was going to talk about is that we're eventually planning on putting a similar UNet++ into an NWP model and using it to parameterize the radiative transfer. In order to do that, we have to make the UNet++ grid agnostic. So on the top, you're seeing the errors for the original model. On the bottom, you're seeing the errors for the grid agnostic model. The errors for the grid agnostic model are a little bit higher because the grid agnostic model includes 2 interpolation routines. And interpolation increases error somewhat, but not egregiously. And you'll notice that the absolute bias for heating rate remains below 0.1 kelvins per day at almost every single height, except that one in the upper stratosphere where ozone absorption is a big thing. So to summarize, our future work involves making the UNet++ grid agnostic in order to actually put this inside NWP as a parameterization. We've done that. We're also currently emulating the full shortwave RRTM with aerosols, trace gases, and ice and liquid effective radii that vary, where we don't assume climatology. The next thing after that will be emulating the full long wave part of the RRTM and then transcribing all of this stuff into Fortran code. And after that, we plan on testing all this stuff inside the FV3 version of the global forecast system model. So thanks.
Thank you very much, Ryan, for a very interesting talk. Our next speaker is Katherine Haynes from CIRA. Welcome, Katherine.
Hi, thank you. Today I'm going to be sharing some work that we're doing here at CIRA in order to simulate satellite or microwave imagery from geostationary satellite data. First, I'll provide some background on passive microwave imagery, or PMI. So PMI is useful because it can penetrate through the clouds and reveal the internal storm structure. So in effect, it can see through the clouds. So as we look at this example on the left, we'll see it fading from infrared imagery to microwave imagery. And we can see that the microwave imagery is able to see the internal structure of this tropical cyclone. In the microwave imagery, the land appears warm relative to the water surfaces, so it appears this green color. And then along with that, low-level moist air masses act to warm brightness temperatures of the water surfaces. So there we can actually see the rain and cloud water emissions that are occurring. And then in contrast to that, we can see that the deep convection appears relatively cold, and this is due to scattering from ice. So that allows us to reveal some of the internal convective structures that are occurring in this tropical storm. So because of these features, passive microwave imagery is useful for hurricane prediction. And it's because the convective structure is critical in order to forecast tropical cyclones. PMI is better for tropical cyclone prediction than visible and infrared imagery for 4 basic reasons. First, there's the identification of circulation center, which is a critical step in initiating TC advisories. Next, it's also useful in positioning the storm in difficult situations, such as during early development stages and at night. Third, it's useful for providing intensification information from convective rain bands. And then finally, it's also useful for monitoring structural changes, such as eyewall formation and replacement cycles. And if we look at the example on the bottom, here on the left, we see geostationary imagery from the visible wavelength. And then on the right panel, we see that overlaid by the microwave imagery. So we can see how it actually can sort of see through the clouds to reveal that internal structure. However, as with any data measurement system, there are always pros and cons to using each of these. So while this passive microwave imagery can reveal convective structure, on the downside, it has to be on polar orbiter satellites currently. So therefore, it has low spatial and temporal resolution, which means actually that there can be gaps in between these images as the satellite has to come over for another pass through. And during that time, it may actually miss some important information on the structural changes that are occurring during the storm. Now, in contrast to this, geostationary satellite imagery can provide visible and infrared imagery on high resolution spatial and temporal coverage. So therefore it can provide near continuous imagery. However, the downfall for these for hurricane prediction is that the upper level cirrus tend to obscure the underlying convective structure. So for this study, what we want to do is we wanted to investigate whether we can use machine learning in order to get the best of both worlds. So our proposed solution is to develop an AI sensor. So here we want to use machine learning in order to generate synthetic microwave imagery from geostationary satellite imagery. And this is in order to fill the spatial and temporal gaps in coverage. So on the bottom of the screen, you'll see a flow diagram of our basic proposed sensor. So if we start from geostationary satellite imagery, we then feed this data into an AI sensor. And from there, we use that to actually make predictions or estimates of microwave imagery. Now, when the polar orbiting satellites cross over, we can then compare our estimates or our predictions against these observations to evaluate our methodology. So the data set that we're using in our study is TC primed, which stands for the Tropical Cyclone Precipitation Infrared Microwave and Environmental Dataset. And this was developed here at Colorado State University by Razin et al. This is a comprehensive 19-year dataset of global tropical cyclone satellite PMI, and it also has coincident geostationary satellite, visible, and IR imagery. The dataset consists of over 126,000 satellite overpasses with more than 1,700 tropical cyclones ranging from 1998 to 2016. Now for this study, we used a smaller subset of this data set. So we were focusing on the Atlantic and East Pacific basins. And also I will only show results from the daytime only and from 2017 to 2019. Now from the subset, we roughly divided this in half into 278 training cases and 272 testing cases. And the results that you'll see for the remainder of the talk will be from the testing cases. So as I alluded to previously, our truth is going to be microwave imagery at the 89 gigahertz from the AMSR-2 satellite. And from this, we are using TC-centered images of 390 by 390 pixels, which corresponds to approximately 4 kilometer spatial resolution at the equator. Now for our input, we are using geostationary satellite imagery from GOES-16. And here we selected TC imagery from the 10-minute scan intervals that most closely matched the AMSR2 overpasses. Now GOES, as we've heard in several talks throughout the day, it has 16 different channels in the visible, near infrared, and long wave infrared. And all of these were regraded to match our the microwave imagery. And in addition to the 16 channels that are on GOES as input to our machine learning techniques, we also used various ratios and differences. So now onto our AI sensor, we used 3 different machine learning techniques. The first was a random forest where we used 1,000 regression trees, and we optimized the input features in addition to the hyperparameters. The next we used was a fully connected neural network, and here we tested the sensitivity of architecture, input features, data scaling, and loss function in order to obtain our optimal neural network. And we optimized these architecture and hyperparameters via a guided search with 3-fold cross-validation. Now, finally, in order to take into account the spatial context, we use convolutional neural networks, or CNNs. And here we tested the sensitivity of the architecture, input features, and loss function. And for our application, we found that the UNet architecture performed the best. Now, if we move on to some results, here are results from Hurricane Michael. On the left, you will see the observations. So the top 2 panels show you the input data from GOES. And the left panel shows you visible imagery, and then the right panel shows you infrared imagery. And then in the bottom of that left-hand section, you'll see the AMSR2 microwave 89 gigahertz data. And this is what we're trying to match. If we move to the right-hand side of this figure, what we see are 4 plots of 4 results. In the top left panel, we'll see the results from the random forest. In the top right is our top performing fully connected neural network. In the bottom left panel, we see the results from a consensus of the top 7 models of our fully connected neural networks. And then in the bottom right are the results from our CNN. And as you can see from all these images, they do a reasonable job at actually predicting the storm here, or the Hurricane Michael. However, we can also see differences between each of these methods. For example, if we start with the random forest, we see it does a reasonable job at actually being able to get the low brightness temperatures associated with the storm. However, it lacks some of the gradients, particularly in the convective bands, and it appears more like rain bands or that we might see. If we move to the ANN, we see that this methodology is not able to actually get those low brightness temperatures, even in the consensus models. However, this method probably does the best at picking up those rain band features on the outer portions of the storm over the ocean. Finally, if we move to the CNN, we see that it kind of appears to be sort of a hybrid between the 2 methods, and that may perhaps providing the spatial information does indeed allow for some benefits. So we see it is able to go ahead and calculate or go ahead and predict the low brightness temperatures. And it also seems to do a better job of getting the gradients across some of these different bands. If we move along to Hurricane Irma, again, the figures on the left-hand side show you the observations, and the figures on the right-hand side show you the predictions from our machine learning methods. And this time, we're only focusing on the neural network results. So in the top 2 predictions shown on the right, we see that in this case, the consensus models, the ANN consensus does indeed outperform the individual model, but we see again that it still cannot predict those low brightness temperatures. Whereas if we move down to the bottom panel, the CNN does a better job of getting those low brightness temperatures and getting the gradients in the convective structure. However, if we take a look, the CNN does appear to have less detail and does a worse job at getting the warm emissions from the rain over the oceans. So finally, if we move into our overall evaluation, what is shown here are histograms of across the entire test data set. So the truth is shown in the green in each of these plots, and so it remains the same. And then each of the colors shows the results from the models that we went ahead and tested. The top line shows you the results from the fully connected neural networks, and then the bottom panel shows you the convolutional neural network results. And as we see from the figure, all techniques perform similarly, and they are able to capture the overall data distribution reasonably well. However, they do have a tendency to overpredict mean brightness temperatures, particularly at 260 Kelvin. And they also tend to underpredict the warm shoulder or emission regime, which is from 270 to 280 Kelvin. If we focus on the ANNs, or the fully connected neural networks, which are our pixel by pixel predictions, we see that these actually underrepresent the cold brightness temperatures. However, as we saw from the images that I previously showed, these tend to show more detail in the maps that it produces. If we then look at the CNN results, by taking into account spatial context, they are able to better represent the scattering regime. So therefore, they are more accurately represent the low brightness temperature, magnitude, and locations. And in some of the cases, they were also more accurately able to predict the eyewall asymmetry. However, they produced less detailed prediction maps. So now I'll wrap up, and this is very much a work in progress. And so what I've shown here are just some trial predictions that we made for Hurricane Ida, which made landfall just a few weeks ago here in the United States. And the bottom shows you the predictions from our different neural network models. So as we work to improve these predictions, there are several things we would like to do. First is to test other custom loss functions in order to improve our shoulder predictions. And next, we would also like to further test and improve our nighttime predictions. We would also like to extend our work to different input satellites and ocean basins. And finally, we plan to extend our work and predictions to different microwave wavelengths. And with that, I thank you for listening to this talk.
Thank you very much, Katherine. Very interesting talk. And we have some time for probably one or two questions. Do we have questions for Katherine?
Folks are not able to unmute to ask questions. All of the questions are over in the Slack space. I can see one. This is from Randy C. Katherine, are you MAE or RMSE from all pixels in the images, or just cloud containing pixels?
I'm sorry, can you repeat the question? My fan is running on my computer.
That's all right. It's in Slack that you might be able to see it as well.
Okay.
Are you MAE or RMSE from all the pixels in the images, or just cloud containing pixels?
From all the pixels of the images. So yeah, so it includes the clear scenes, as clear portions of the scene as well.
I have a question. When you are talking about consensus neural net, how many neural nets are included in this consensus?
We went ahead and tested that with all the different combinations and numbering from 1 to 8, and we found that 6 to 7 models did the best. So the results that I showed used 7 for the histograms, and then when I went ahead and made the loop that I showed at the end, because it took longer to go ahead and make the predictions for 7 models, we went ahead and just used 4 models for that to include in the consensus.
Okay. Thank you very much. If we have no more questions, then we will move to the next speaker, Timothy Higgins from NOAA. Welcome, Timothy.
Hello, everybody. My name is Tim Higgins. I actually don't work at NOAA. I'm a second-year PhD student at the CU Boulder Department of Atmospheric and Ocean Sciences. Today, my talk is going to focus on tracking atmospheric rivers in a large climate data set. And first, I would like to give a special thanks to everybody who contributed in some way. So for those of you who are somewhat unfamiliar with atmospheric rivers, are these long, elongated corridors that move through the lower troposphere and play a vital role in Western US climate. There's a fairly high degree of uncertainty in how a warming planet may affect them in the future, which is why I'm trying to understand how they might change in a large climate data set. In order to understand anything about them, the first step needs to be having a method of tracking them. Traditionally, empirical heuristics have been used to track these events. However, a lot of them rely on variables that aren't always available, and they do use a lot of computing power. One more recent alternate approach has been using semantic segmentation. In addition to large climate data sets often use smaller domains in order to save computing power. And semantic segmentation has only been experimented with on global domains. So I'm going to be looking into how semantic segmentation might work on a regional domain. I'm using a very unique data set. It comes from the Weather at Home project, which uses computing power from thousands of different volunteers' computers. I have 2 terabytes of data, and I'm using integrated water vapor, zonal and meridional wind at 850 millibars, surface pressure, and precipitation rate as my inference data. So there are 2 different deep learning models that have successfully been used so far to track atmospheric rivers. The first being DeepLab v3+. It is a state-of-the-art, very high-performing model that uses a lot of computational power and takes a very long time to run. So an alternate approach is using CGNet, which is a lightweight neural network. It has about 2 orders of magnitude less parameters than DeepLab v3+, and is much quicker. So in the past, DeepLab v3+ and CGNet have both been used to identify objects in cityscapes. So you can think with a self-driving car, identifying where maybe there's a traffic light or another car on the road, or maybe a person on the side of the road. Here, I'm applying a similar idea to the training data. 80 different weather and climate scientists participated in a hand labeling campaign where they looked at spatial images of the globe and made a hand-drawn contour in any area where they felt there was an AR, and did nothing where there was not an atmospheric river. This training set contains about 500 feature label pairs. So when I got the output of my climate model, I had the domain that you see at the bottom of the screen, this large domain. And since CGNet requires that the inference set and the training set have the same exact domain and resolution, I had to pick one of these 2 domains to train it on, while that larger domain, of course, has more training data. Since atmospheric rivers do occur over the Atlantic as well as the North Pacific. The smaller domain is much quicker to run the model on, and the smaller domain also has a climatology much more similar to the region that I'm looking at. So I ran CGNet when trained on each domain and immediately found that there is a very significant difference in the results. The smaller domain detected atmospheric rivers about 10 to 12% more frequently than the larger domain did. So then I looked at an eye test to see if they were at least both to some degree doing the right thing, and it seemed to pass. They are both definitely detecting atmospheric rivers. So I decided to do a statistical analysis from there, since there is no real truth as to what an atmospheric river is and what it's not, according to empirical heuristics, since there's no really strict definition, the best I could really do was compare it to other popular detection algorithms. So I trained CGNet again on 20 months of Merit2 data from 2006 to 2015, and then compared those results to the average results of 5 other popular detection algorithms. And here what you're looking at is you're looking at the percentage of grid points that overlap with CGNet trained on each domain compared to the 5 other detection algorithms that I looked at. And here we can see that when training on the smaller domain, it's actually slightly, there's not a big difference, but training on the smaller domain is actually slightly more consistent with other algorithms than the larger domain. But overall, over 96% of the time, the grid points will match. So then I looked at a comparison when trained on each domain to each algorithm individually, and found that, again, when trained on the smaller domain, that was slightly more consistent with the other algorithms compared to when trained on the larger domain. However, it is very much algorithm dependent. So you can see that the larger domain was actually more consistent with GAN-MulWG, which is one of the most popular detection algorithms. You can see positive values here indicate that the smaller domain was more consistent. Negative values indicate that the larger domain was more consistent. So then after that, I looked at a different metric. I looked at mean intersection over union, which is the area that 2 results overlap with ARs divided by the sum of the area where they overlap plus the area where ARs are detected and do not overlap. For reference here, when 2 expert labelers' labels were compared to each other, they had a mean IOU of about 0.34. So very uncommon to have an IOU of more than about 0.3. Again, we're not comparing it to truth here. We're just comparing it to GAN-MulWG, which is a very popular detection algorithm. And we can see that CGNet trained on both domains is fairly consistent with other algorithms when compared to GAN-MulWG in terms of mean IOU. I then looked at the bias and found that there's a fairly large negative bias of CGNet. Again, compared to other algorithms, it's not compared to truth. Near the coast and then off the coast, there was a very positive bias. This likely occurs due to most of the other algorithms being based off of relative IWV and IVT thresholds, while CGNet was really more trained on absolute thresholds, which have a very significant impact once ARs reach the coast. So from there, now that I have identified ARs in my data set, I can now really start looking at how a warming planet could impact them in the future. And in conclusion, we found that semantic segmentation is a useful way to identify atmospheric rivers in large data sets and a very efficient way to do it as well. We found that ARs can be identified on regional domains in addition to global domains. We found that at least this data suggests that the climatology could be at least as important as the amount of training data in order to be consistent with these other algorithms. And we also found that accounting for this relationship between moisture and topography, as I recently just showed in the bias slide, could remain a challenge with semantic segmentation. And that's all I have today, so I can answer any questions that people have. I don't have a Slack up right now, but I can bring it up.
Yes, thank you very much for very interesting presentation. We have time for a couple of questions. Do we have questions?
There's one in the Slack. I'll read it for you, Vladimir.
Okay, thank you.
It says replacing the Deep Lab V3 with simpler neural network. Are you indicating there are redundant complexity in the Deep Lab V3 for this task? Or does it mean that the CGNet has some feature that makes the learning more effective?
So I am still working on comparing CGNet to DeepLab V3 Plus, but so far I was able to show that CGNet does compare reasonably well to other algorithms, but that's something that I'm working on next. I do see another question here.
Okay, please read it and answer.
Christina Kumar says, your work reminds me a lot of my own and how evaluating the ML performance can be tricky with truth labels having potential uncertainties. There was a talk yesterday that mentioned comparing detection algorithm truth labels to ML performance like this is in terms of uncertainty. You could attempt to give your labels a certain certainty value and then have analysis of the ML model based on those with certainties that you deem high enough. I found this interesting and perhaps you might as well. So actually it's not a question, it's a comment. But thank you for that. I'll definitely think about that and maybe look at that talk if I can.
Okay, I have a question. Do you have any way to control complexity of your net? Because in your situation, I think it's very important to prevent overfitting, producing false results because of that.
So can I get this clear? You're asking, is there a way to control the
complexity of your neural nets which you use?
Right. I could potentially try adding in more parameters, but that's not something that I have looked into yet, so I can't talk on great detail about that.
Okay, thank you. So thank you very much again, and our next speaker is Nachiketa Acharya. Welcome, Nachiketa.
Thank you. Can you see my screen?
Oh, yes. Okay.
Yes, looks great.
Okay, thank you. So today our talk on using the GAN for multisite weather generator, which is, if you remember, the first talk on the GAN for downscaling. And this is slightly different. And myself, Nachiketa from Penn State, and my co-author of this talk, Kamban from VIII, and he's the main person behind this whole concept and the code. And we work on this things from last 3-4 months, and it's a very interesting work and ongoing work. We just want to share this thing, couple of results and concepts so that we can get the feedback for our main goal. Excuse me. So if you see the title, so it's on the Generative Adversarial Network based on multi-site weather generator. So just for this audience, if you don't know what's the weather generator, it's actually a stochastic model which produces a long time series of weather variables that have the same statistical properties coming from the data. So that means, like, suppose you have a historical data and you want to fit that data in a distribution, and then from the distribution you can generate more, like as much as you can. The question is for what? Why we need that kind of model? So it has a wide application, especially in the hydrometeorology, agrometeorology, where for those crop model or the hydrology model, it's important to have those daily data. So it can be used for stochastic disaggregation. It can be also used to fill the missing data. It can also be used for the statistical downscaling for climate change impact. So it has a wide application in terms of hydrology or any kind of impact modeling where the climate is a major impact factor. On that, it's not something very new work. It's actually started from 1852, very old paper where people try to predict the rainfall, wet and dry sequence, this and that. But in this particularly weather generator, the famous work is actually by Richardson in 1981, where they are talking about generating the rainfall in solar radiation, this and that. So it actually has a vast literature and it has so many existing models. Mostly people are interested in the precipitation because that's the complex, because it has two stages. First, we have to model for the occurrence, which is a discrete data. And then if it is rain, how it will be like fit in a distribution or resampling. So it has a lots of different method. And then people are also adding more variable like temperature, solar radiation, and connected with all the variables. So just a little bit of the concept, like what's the classic approach? For the rainfall at least. So we start with the sequence of rainfall and fitting a Markov chain kind of model because it's based on the stochastic modeling. And then if it is rain, go for the distributional approach. Although there is a resampling approach, but this is like a very basic Richardsonian method and just a little bit of more. So basically from the historical data, we know all those transition probability. And based on this transitional probability, we start picking the data from the uniform distribution and give some condition that if the value of the random data is less than this, it's rain, if not rain. And then it's go on. And at the end, we generate lots of binary data, which is 0, 1. So 1 means rain, 0 means no rain. And then from that, we draw the random number based on the distribution, which is fit from the rainfall data, and then get like something like this. So it's from the 0, 1, we now have the data in terms of 1 where the rain and no rain. So that's basically the concept of using a parametric method on the weather generator. Now it has lots of limitations. Most of the limitation is like it's underestimate the interannual variability. It also less efficient simulating the extremes. So most of the distribution are very good in the capturing the descriptive statistics or mean or the central tendency, but they're actually underpredict the extremes. But the biggest limitation in terms of the application is like a single site. That means suppose we have a huge watershed or huge data set and we have to you have to develop this method for all the different site. But the limitation of most of the weather generator, they are very independent. That means like each weather generator fit for one single site. There's no information for the other site, which is very important in terms of the impact study. Like if some area has some impact of the local rain system, that should be also impact of the other system. So that's what the multi-site is so important, because then you can capture the spatial variability or correlation structure of the spatial variability. On that point, we started thinking about whether any kind of machine learning method can help us to actually minimize those limitations based on the existing methods. On that, we started with the generative adversarial network. The interesting thing, like GAN is one of the improved generative methods, which actually include two systems like sub-models. One is generator and discriminator. It's something like, suppose from the random noise, you prepare some fake data, and then there is a discriminator who can tell us which is yes or no. That means like it has a classifier, which is discriminator, and it's also had the generator. The interesting thing is like, Jan LeCun, which is the director of Facebook, he said that this is the most exciting development in the last 10 years. And I have seen like almost everywhere, wherever you see the image processing or any kind of automatic photo image process or voice process is actually very popular nowadays. And we also see like in the first talk, like in our field, people use it for the low resolution to high resolution, that kind of downscaling. But we are using in a different way. So here, the concept, like, first the real samples, then you train the discriminator, then there's a generator, then you can like discriminator can say, and it's keep on working in adversarial game until unless discriminator generator full discriminator. That means discriminator cannot find any difference. So a little bit of math, although we see in the first talk, but what we understand from the math, the first point is like discriminator prediction from real data. So it always, they wants to improve, like maximize this term because in terms of the prediction, and the other part is actually the discriminator prediction from the fake data. And discriminator want to minimize this part, but the generator wants to maximize this part. But as it is 1 minus, so at the end, is whole function, we have to be maximized. So that's mostly like a loss function we are using for the value called value function. So basically, this is the structure, but it can just, pictorially, you can like to start with the network. None of the discriminator or generator understand from the what should be their goal, and then gradually it learns from the data, and at the end, it looks like this. That means like that function is like Haupt. That means probability of 50%. That means discriminator cannot understand or cannot discriminate between the real and fake data. So based on that, we try to use in GAN, but question is why? Why you use GAN for weather generator? As we already talked about the limitation of the other weather generator, but here is that something we're really looking for. One is it is non-parametrics, that means no assumption over the distribution on the data. And second thing is like although some weather generator based on resample, but resample does not produce a future extreme which is not in the historical data. So that's a bigger limitation of the resamples. So that's what we use the GAN, and also it's a very realistic because it's used for the different medium image processing, and the image look like very real. So we're expecting more realistic data. And also it works for the smaller data set because it's a semi-supervised learning. So it can also work if we have a less number of data set. On that note, a case study we can see. So there is actually a real case study we use for the New York City primary water supply. So the New York City primary water supply comes from the upstate reservoir. They have like 6 watershed, and since 18th century, they want to reserve this area. They want to minimize the cost of the filtration. They want to reserve this thing. And it's actually, if you zoom that area is actually a combination of 6 watershed. And it's a very interesting, it's a mostly like gravitationally that water comes to city, and it's almost cover 95% of the system. But the question is why you are interested on that? Because the recent study shows this area, mostly the northeastern part, actually having more rainfall. And also from the projection, we can find that is actually having more extremes, and which may impact a lot in terms of the increase of sediment erosion, increase of nutrition loads, change in the annual cycles. As I mentioned, this whole area is actually very natural. There is no huge cost for the filtration. So impact of extreme events will be huge in terms of the water quality in future. So on that note, there is already a study going on. Some of them is like we publish a paper. So what we do in the earlier study, we actually find it out which weather generator works, but using the traditional method, using the single site. And then we are actually using that weather generator combined with the watershed model and doing some kind of impact study. But keeping the same example, we want to use, as I said, like multi-site weather generator has huge impact on this side because we can't model the weather generator independent because they are like only 4,000 square kilometer area, very small area. So that's what we want to test this GAN-based weather generator in the same area if it is actually giving any value-added addition. So the implementation part is mostly like my colleague Kamban did that. So we actually use 3 layers of sequential models. First, the latent vector would comprise 20 values. From normal distribution, we choose the noise, and then you use a popular ReLU activation function for the hidden layers. We use the mean absolute percentage error for the loss function. And to prevent the overfitting, we also adopted the dropout regularization techniques. And at the end, we actually generate 10,000 synthetic data set, which is actually features corresponding to those 6 watershed. And to start this process, we go at the monthly scale. We don't go to the daily scale because we really want to see whether this concept works or not. On that point, I can show some of the preliminary results. So this is like a monthly mean simulation and actual from all the watershed from the last 60 years of data. So we can see the box plot looks very similar. We can't even discriminate, but there is some outliers we can find which is not captured in synthetic data. But if you go a little more quantitative way, where you can calculate the mean, standard deviation, and different percentile, and as we're interested in extremes, we can find that this weather generator is actually very much well to capture those extremes in terms of 75th percentile and the max value, which is because this is more important in this study. And we are very actually happy to see that kind of summary statistics. Now, as our main goal to capture the correlation among the watershed, we also calculate the correlation among different watershed from the actual and the synthetic data. And you can see is amazingly it's capture all this correlation. And if you see the little difference is actually it's a non-significant difference at all. It's like 0.93, it was 0.96. And it can also be improved if we tune the more model, more hyperparameter or parameter things. But it's just like a simple GAN. We don't even use it in conditional GAN or other things. So to start that concept, we are very much happy that this GAN-based weather generator actually works. On that note, we are actually thinking about in future, if we can modify for the daily scale where the temporal part comes, so we can actually also model that the sequence of the rainfall, and also try to include more climate variables. That means like instead of multi-site or the correlation keeping in the different space, we also want to keep different variables and keep the correlation between, let's say, rain, temperature, wind, solar radiation, and it will work in that way. So we don't have to do a different stage of modeling. For example, in the traditional approach, they first model the rainfall, then they model the temperature based on the rainfall, or first they go for Tmax, then they go for Tmin. So you don't need any kind of a sequential modeling in this case. It can go in at the same time, but it takes a little bit of time for training the model. But once it's trained, the generator is like a very quick. So on that note, I should say thank you for listening the last talk of this day, and any feedback, anything, please put in the Slacks, and where me and my colleagues come and can reply. Thank you very much.
Thank you very much for this presentation. So we have already one question. We have time for questions. General GAN question: how does one access GAN output? How does one make sure that the GAN doesn't simply output samples from the training data set? They will look realistic.
First of all, like there is lots of way to assess the GAN. We can, as you say, like summary statistics or other things, or we can actually compare with the traditional methods. And I'm not sure about what does it mean by the out of sample, because the whole idea of the generative is like out of samples, new extremes. So while we are training the GAN, we are using the training data set, but while it's generating the new data set, it should also come from the out of sample. So I'm not sure about the second question, but there's a lots of different way to access the GAN.
Okay, I have a question. Are you going to consider different architectures? I mean, in addition to GAN, some different AI architectures. Are you going to try other?
Can you please repeat?
Are you going to try other AI architectures in addition to GAN?
The point using the GAN, because the generative and the adversarial games, because we can use some others method like traditional neural network, but theoretically the improvement of GAN, because the discriminator part, so it's actually always let us know whether those random data from a synthetic data set where is more close to the real or not. So that's why we go for the GAN. We see like some, I think one of the paper available, they are using multi-layer perceptron for the stochastic weather generator. But again, the problem is there's a huge overfitting problem if they use more of the hidden data. And here, as we use a different way, so there's no overfitting problem. At the same time, it will be more close to the real data.
Okay, thank you very much. And thanks to all speakers and listeners, and have a nice rest of the day. And we can continue discussion and asking questions at Slack. You know, welcome to channel 03, Weather and Climate. Bye-bye.
Thank you to all the speakers. Please continue the discussion on Slack and join us for this evening's poster session in the Pico chat space.